So in this video, I'm going to go over differentiation from first principles and try to introduce you to differentiation in calculus. So let me start with a little scenario here. Let's say we were given this little function here, f of x, all right? And we don't have to say exactly what it is, but let's say it's some curve here. This curve is the function f of x. Now let's say on this function, right here, we have some point A. All right, we don't know exactly what point it is, it's just some point A. And if we go some distance, h, away from A, we'll get to the point A plus h quite clearly, because it's going to be the distance A plus a distance h to get to the point A plus h. Now on our function f of x, the y-coordinates for these points are going to be the following. We're going to have the coordinates A, f of A, right? And then over at A plus h, we're going to have the coordinate A plus h, f of A plus h. So this is all well. It's pretty clear that we can see that directly from our little scenario here. Now let's say we wanted to find the slope of a secant line connecting these 2 points, which we would know would be the average rate of change between them. The average rate of change is the slope of a secant between any 2 points. So if we drew a slope line here, try to make it as straight as I can, and it connects these 2 points together, we would know that the slope of this, the slope of the secant, messing up my spelling here. Yeah, so the slope of the secant would be equal to the change in y over the change in x, right? It would be this delta y over top of this delta x. That would be the slope of the secant line. So if we write a little equation for what the slope would be, we can express it in terms of the function f, because we know what delta y and delta x would be. We can say that delta x would, or well, we'll start with delta y. Delta y would be f of a plus h minus f of a. That is the change in height of the function f of x. And then if we write that over top of the change in x, we would have a plus h minus a. And you can see that quite clearly here. This is the change in height, and then this here is the change in x. So this function represents the slope of the secant between a and a plus h. So now, if we simplify this a little bit, we'll find this is equal to f of a plus h minus f of a over top of h, because these a's here will cancel out. So we now have a function which will model the slope of a secant line between some point A we pick and then some distance h away from it. Now, let's say we had a different problem. Let's say we wanted to find what the slope of a tangent line at x equals a would be. And we know finding a slope of a secant between 2 points is easy. We have a formula right here. But what about the slope of a tangent? And so there's a way that we can actually estimate this, and we'll find the exact value of the slope of a tangent at point A. So as we can see here, let's say we were to take the value a plus h right here and make it smaller and smaller and smaller, make the value of h so small it gets incredibly close to a, right? If you keep going, we get to here. We're going to get to a point where the slope of a secant line will be so slight and so very close to the actual slope of a tangent at point A that it effectively will be that. And in fact, in the limit, as this delta, as this h here, approaches 0, it will converge exactly to the slope of a tangent at point A. So this is the way that we can find the slope of a tangent at point A, is by making h as close to 0 as possible in the limit as h approaches 0. So what we get then is that the slope of a tangent at point A, this is equal to, let's see right here, it is equal to the limit as h approaches 0 of f of a plus h minus f of a over h. That is the slope of a tangent at point A. And what we'll see, this is actually a function. And what we write this function as is f prime a. This is called the derivative function, because we can put in any point A on our original function f of x, and we can find the slope of a tangent line at that point. And this is incredibly useful in calculus. So what we say is that f prime a is equal to the limit as h approaches 0, f of a plus h minus f of a over h. And this is the first derivative. This is what this formula here is called. And it shows the slope at any point that we want. So let's go through some examples of where you could see this being asked in a question on a test. So let's do a quick example here. Find the slope of a tangent at x equals 3 on the function f of x equals x squared. So now this is pretty easy because we can use the formula that we derived up here. We can say that, well, f prime 3, well, for now let's keep it f prime x, I'll put 3 in after. F prime x will be equal to the limit as h approaches 0 of f of x plus h minus f of x over top of h. In this case, our function f of x is x squared. So f prime x will be equal to the limit as h approaches 0 of x plus h squared minus x squared over h. So now we can expand out this binomial here, and we'll find that it's equal to the limit as h approaches 0 of x squared plus 2x h plus h squared minus x squared over h. And we can cancel out these common x squared terms here. And so we'll be left with the limit as h approaches 0 of 2x h plus h squared over h. And again, we can also cross out these h's. And this is okay because if you remember the property of the limits, it's okay if the limit's not actually defined at a point h equals 0. It's only the behavior as it approaches 0. So it's perfectly okay to cross out these h's. And so we're going to be left with the limit as h approaches 0 of 2x plus h. And if we evaluate this limit, we're going to be left with 2x. So this means that f prime x, the function which models the slope at any point x on f of x, is equal to 2x. So now if we want to know the slope at the point x equals 3, all we got to do is substitute in our value. So we're going to get f prime 3 will be equal to 2 times 3. And so the slope of a tangent line on x squared at x equals 3 is going to be equal to 6. And so calculus and then differentiation gives us a very easy tool to find the slope of a tangent at any point. So let's do another example here. So let's say find the derivative function of f of x equals x squared minus 3x plus 4. In other words, find the function which will give you the rate of change at any point on f of x. Well, we know that the derivative function f prime x is equal to the limit as h approaches 0 of f of x plus h minus f of x all over top of h. H is the little delta x. It's the amount to the right of our function that we're going to go. And now if we substitute our function in, we'll find that f prime x is equal to the limit as h approaches 0 of x plus h squared minus 3 times x plus h plus 4. Put some square brackets around this. Minus x squared minus 3x plus 4 all over top of h. So now we just have to do a little bit of algebra and simplify this a little bit. So this will be equal to the limit as h approaches 0 of x squared plus 2xh minus 3x minus 3h plus 4. minus x squared plus 3x minus 4. So we expanded out this binomial here to get this. Oh, forgot the plus h squared there. It's a good thing I checked. Yep, expand that, you get x squared plus 2xh plus h squared. And then expand this negative 3 in to the x plus h to get minus 3x minus 3h. Add the 4, and then subtract, expand out the negative here into this trinomial here to get negative x squared plus 3x minus 4, all over top of h. So keep simplifying here. We'll get the limit as h approaches 0. And we'll notice that a few things cancel out from the top here. These x squareds, they'll go away. The 4 here, those can cancel out. This 3x, those go away. So we're just left with 2xh plus h squared minus 3h over h. And now we can common factor out an h here. And it's okay to do that because the limit doesn't actually need to be defined to exist at h equals 0. So we'll get the limit as h approaches 0 of 2x plus h minus 3. And if we evaluate this limit, we're going to get 2x minus 3. So what this means is that the derivative of f of x equals x squared minus 3x plus 4 is equal to 2x minus 3. This is the derivative function of f of x. So that's a quick overview of differentiation for first principles and how you can find a function which models the slope of a tangent at any point that you want on a function that you know.